Bruh.
All right, so welcome to today's lecture. We're going to be doing Intro to Machine Learning.
Did we start?
I did start. It started right, Maya? Yeah, okay. We're doing an introduction to machine learning, so we're going to talk about linear, logistic regression, which are just like sort of some more like algorithmic stuff, and then we're going to start and just touch on neural networks, and then we will probably review what we talked about today, and then complete like the basics on neural networks next time. But first, there's a reminder first. We've got Idea Hacks, which is coming up next weekend. It's going to be hype, so if you're signed up, get really excited for that. I think signups are over, so kind of know if you're doing it or not. But just a reminder, it's going to be fun. I'm going to do it. Frank's probably going to do it.
We didn't do the date for GB Olympics,
Oh.
but it's fine.
Yeah, sorry. This is not right. Sorry about that. But GB Olympics are happening next week. So if you're in a GB, who's in a GB? Woo!
Damn.
No one's in a GB? Okay, never mind. We'll move on. But okay, I guess video people. Yeah, that's happening. Is going to happen next week. So check it out. Check out the URL for some more info. Highly recommend doing that.
Anyway, hello, I'm finally in frame. So anyway, first of all, we're going to talk about the basics of artificial intelligence, and we're going to start by actually defining what that is, because it's kind of a nebulous term. We advertise this project by saying you guys are going to be able to drop lots of random buzzwords into your resumes that the corporate bootlickers will like. So let's start with artificial intelligence. Artificial intelligence allows computers to perform tasks that require human-like intelligence. So basically, the computer is going to learn how to think like a human and do tasks that we sort of take for granted because we don't really think about how our brain does things, but the computer needs to be taught how to do these things like driving a car. So there are three primary types of machine learning that sort of are all under the umbrella of machine learning. So the first is supervised learning, which is basically when you have a lot of data, your data is already labeled with the correct answer, like you have inputs that are labeled with the correct answer output, and your goal is to basically teach the computer to figure out a pattern in the data, and then that way, when you give it new data that it doesn't have a correct answer labeled, the computer can then figure out what the correct output is. The next type is unsupervised learning, which is basically you have data but it doesn't have labels or anything, or there's no correct answer. You're just teaching the computer to kind of draw its own conclusions. So this is done by something called clustering, which is basically taking the data points and the computer sort of figures out arbitrary groups to categorize the different data points into. The last type is reinforcement learning. This is where the computer learns by making mistakes, evaluating itself. Sometimes it'll be pitted against other models to evaluate, so they'll evaluate each other. And basically it improves by making mistakes and learning from them. A lot of modern chess, and other game artificial intelligence models, if you are familiar with them, they use reinforcement learning to train, because they train by just playing the game over and over, evaluating their performance, and making slight changes that push them towards the optimal solutions. So this is the machine learning pipeline. It's kind of a long process, but the main thing you have to understand is we start by gathering data. We clean it up to do things like remove the outlier data points if we can find any obvious ones. We format it by converting it to a computer readable format. We add the labels if it's supervised learning. And then we go into the actual machine learning part, which is where we train the model, we validate it on some actual data points that we have. Then we go back, train it some more, validate. We keep doing that until we reach some satisfactory performance on a validation set. And then once we've done that, we can test it on our actual real world data. And if the model is up to scratch, then we can actually go ahead and use it in the real world. So we'll start by talking about the most basic example, something you've all probably seen before in a math class. It's linear regression. So this is a line of best fit. All of you, I'm sure, have seen this before, but you probably aren't familiar with or are a bit fuzzy on the process by which we actually find one. So we're going to talk about that. It's actually just the simplest form of machine learning. This is how we basically draw a line that best reflects a pattern in data points. So we're trying to find a linear function, a line that is the best fit for the data, that accurately represents what the inputs, how the inputs map to the outputs as closely as possible. However, in order to determine what best fit means, we have to come up with a loss function. A loss function is just an evaluation of the error that the prediction line is making. If the error is very high, like the predictions are way off, then our loss function is going to be very high, and the model should learn from that and improve itself. If the loss function produces a very low value, we know that the model is doing well. For linear regression, we typically use the mean squared error function, which looks like this. It's a little bit complicated, but the general idea here is that y hat generally refers to a variable that's a predicted output from the model. So it's not the actual data points, but it's the data points as like the model is predicting them. Y is our actual like true values. So like if we have x, y pairs that we feed into our model, y is the true value, and n is the number of data points. So basically what this is doing is it's calculating the error, which will be more evident in this diagram. It's calculating the error between a data point and the predicted value, so y minus y hat. It squares it to eliminate the negative sign, and then it does that for every single data point and averages them all together. That's why it's mean squared error. It's taking the mean of the squares of the errors. Any questions so far? Cool. So, now we're going to start talking about gradient descent. This is the process by which we actually train our line, the process by which we reduce the error and the loss function. So our y hat, we can rewrite that as ax plus b, the formula for a line. So now we can substitute that into our mean squared error function. It looks like that. So in order to basically optimize this line to find the best possible line for the data, we need to find the best possible values of a and b. And the way we do that is by using the gradient, which is a term from multivariable calculus that you might be familiar with if you've taken 32a or 32b, or math 32a, 32b. This is the gradient. It's just a vector. You don't need to really worry about the fact that it's a vector for now, just the fact that it uses the partial derivatives of the loss function with respect to a and b. By the way, just to confirm, does everyone understand what a gradient is? Cool. So this is our loss function plotted against a for starters. It looks like a parabola because the mean squared error function has a square in it that basically makes it a parabola. We've just added 2 points on it. When the partial derivative with respect to a is greater than 0, which is that point on the right, that causes, that basically means that if you decrease a, so if you move a further to the left, it causes the loss to decrease. As you can see, the minimum loss value is right down the middle of the parabola. If you decrease a by going towards the left, the loss decreases, which is what we want. On the other hand, when the slope of the loss function with respect to a, the partial derivative, when it's less than 0, you have to increase a in order to decrease the loss. So by using these two simple facts, we can essentially work towards a minimum value of the loss function very gradually. These are what's called gradient descent steps. So once we know the gradient with respect to a, we update the value by basically multiplying it by a constant factor, subtracting it from the original value, and that's our new value of a. And then we just keep doing that over and over. So we start with a completely random value of a, and then we calculate the gradient, determine whether we have to increase or decrease and by how much, and then we subtract that from the original, and we just keep going. As you can see, like if we start from the value in the very top left, by doing these gradient descent steps over and over, we can slowly get to the center, the minimum. Any questions so far?
So we just set alpha so that we don't just oscillate back and forth, right? So we'll eventually reach.
I'm getting to that. So alpha here is the learning rate. It's basically a value that we set in order to make the to tell the gradient descent and how susceptible it should be to changes in error and how quickly it should, how large its gradient descent steps should be. So to demonstrate, we pick the value of alpha ourselves. It's called a hyperparameter because we have to contribute this parameter to the model. If the learning rate is too large, you may never converge to a minimum. As you can see, the gradient descent steps here are very large. So it goes across and back, and in this case, it's actually diverging from the minimum rather than converging, which is not what we want. This happens if your learning rate is too large. On the other hand, if it's way too small, then the training will take too long because your steps are so small that you have to keep doing it over and over to eventually get to the minimum, which you will reach the minimum eventually, but it'll probably take way too long and you don't want that. Any questions? So to quickly summarize, these are the equations that we've looked at so far. We included this slide so that when you're referring back to the slides while doing the lab, it'll be useful. That is the formula for the line of best fit that we're using to predict our new values. This is the mean squares formula. These are the partial derivatives. We can derive them if you want, but it's just a very simple partial derivative with respect to A and B.
Better do it yourselves as an exercise.
Yes. And then finally, we update A and B by using the learning rate and the gradient, and we take a gradient descent step in the appropriate direction.
So I guess, does anyone want anything clarified on the basis of gradient descent? Because now we're just going to be building off of this for most of the rest of the lecture. Everyone understands it perfectly. Okay, cool. All right, so now we're going to talk about what we do when we have more features. And really, this is just going to be modifying the equations we saw just before. So a feature is really an input to our model. So in the previous example, we had one feature. That feature was x. We were plugging it into ax plus b, and we were getting an output of y hat, which we were then using to try and predict y. But you might have multiple features, right? If you're trying, you could try and be predicting, temperature based off of humidity. But if you also have, length of the day, you might also want to plug that into your model. So we can use all of these to create a more complicated model. So we're going to go over some terminology for what we're going to do before plugging these new variables into our modified equations. So now we're going to be using matrices, which hopefully people remember from 33A and a bunch of other classes. So now we're going to be replacing A and B with theta. So F is going to be the number of features, and N is going to be the number of data points. So theta is going to have a size of F plus 1. So in the previous example, F was 1, and our theta was size 2, right? It had A and B. So now our theta is going to, if we have 2 features, we're going to have a theta of 3, right? 2 weights for each feature, and then a constant bias term.
Real quick, has everyone taken 33A? Is there anyone who has not? Okay.
Right. And if you need some
additional
help,
clarification, feel free to ask anything.
Yeah. Do you understand matrix multiplication and transpose?
No.
Okay.
All right. Don't worry about it.
All right. Well,
transpose is not as important.
Yeah. Okay. Transpose is literally just flipping the matrix. So all the rows become columns, and all the columns become rows. So that is the short version. But it won't be as important. All right. So x before, right, it was just one singular value. Now it's going to be an n by f plus 1 matrix. So every single row is going to be one data point, and every column is going to be one feature. You'll notice it's f plus 1. The last column is going to be a column of 1s, and these are in order to multiply with the bias term from theta. So we'll see this a little bit more clearly in a second, but right now x is n by f plus 1. Y is just going to be literally just a vector of all of the ground truths, and y hat is going to be a vector of all of our predicted outputs. So this is going to be the basic equation, y hat plus x theta. So now we're going to do a quick example to just make sure people understand what's going on. So we're given this data, all right, on several different types of books. What we're trying to do is predict the rating based on how long the book is, when it was published, how many dragons are in the book, and whether or not it's fiction. Okay. So first, let's just start. Does anyone know what big N is going to be from the previous slide? Based on this from this data set. Justin, what is N going to be? Yeah, okay. N, so F, right, is the number of features, and N is just going to be how much? It's just going to be the number of data points, right? So here,
We have 6 data.
6 data points, right? Okay, and then F is going to be
6 or
4.
5?
It's going to be 4.
4.
Rating is what
Rating's
we're
the
trying to
result,
predict. Yeah,
not-
rating is
not
what
a feature.
Yeah, that's
Yeah.
that's our predicted output. Okay, so knowing that,
Okay.
who knows what X is going to be? Jennifer, you know what? Oh, sorry.
So like the pages your dragon count is fiction and then a column of ones?
Sorry, say that again.
Is it like pages your dragon count is fiction and then a column of ones?
Yes, that's what X is going to look like, and who knows what Y is going to look like? This should be. Don't overthink this one. Someone else? I know, Jennifer. Do you know what it is? What?
Like the rating?
Yeah, it's just going to be straight the ratings. Nothing changed about this. So yeah, very good. X is just going to be this matrix that looks, and again, column of ones right here. Y is going to be the column of no ratings. Okay, so now we're going to build up this. Now we've trained our model already. This is the model that we made for this data, and this is what it looks like, right? Where A, B, C, and D are the things from before. They're pages, year, dragon count, and fiction. So we're going to multiply those values by these constants. And then we've got this one bias term at the end, and we are predicting these values. So who knows what theta is going to be?
A, B, C, D. No, is that not? The way-
Sure, go ahead.
It's the thing before.
It's
Sorry?
it's the constants you multiply them by and then the bias is the last entry.
Yeah. So it'll just be each of these constants and the last one. And then what about y hat?
The
Am I-
predicted.
Yeah, it's just going to be straight the predicted value. So that's very straightforward. And now just to illustrate again how this matrix multiplication is going to work. So if this is one data entry, right? When we do matrix multiplication, this is all going to come out to one term in y hat. We're going to multiply the first term here, and as you can see, this 1 gets multiplied by the 0.1644. That's right up there. Okay, so now we just basically rewrite all of our equations with these new matrix forms. So this is the equation from earlier, the y hat is equal to x plus theta. Now we're going to turn our mean squared error into this equation, which is actually going to be the equivalent, where we're taking the transpose of y minus x theta, which again is going to be the same as y hat up here. Take the transpose, multiply it by itself, and that's going to give us the squared number. It's basically like taking the dot product or the dot product with itself. And then these are the gradient. It can be rewritten as this, and this is going to be a vector where each entry is a partial derivative with respect to one of the item or one of the weights in theta. And then this is just the same. Do we have questions on this part?
It's okay if you do. We have plenty of time.
Yeah.
If there's something that you think would be too long to explain, we can still explain it.
Okay, so this is how gradient descent is going to work for linear regression. However, we lied to you a little bit. This is not the only way to find best fit lines. There's also a closed form solution. So closed form basically means that we're going to arrive to the minimum in like a finite amount of time. Right, because when we do gradient descent, we're iterating over and over doing the same operation over and over again, updating theta. But we can actually find a optimal theta for linear regression, and that is if you look at this equation right here. You may remember from calculus that at the minimum, the gradient is going to be equal to 0, and fortunately for us, the loss function is going to be concave. So there's going to be one global minimum. We won't be able to do this for most other forms of machine learning, but there will be a global minimum for us, and we can solve it by setting this delta L, or sorry, this nabla, I think it's nabla L to the gradient of the loss function to 0. So if we set this to 0 and we solve for theta, we're going to get this term right here, which will give us the optimal values of theta, which will give us the least error for our linear regression function. It is important to note, though, that this equation, right, is very computationally intensive, right? There's a lot of matrix multiplication. If you have a lot of data, it could take a really long time. Matrix multiplication is really expensive. So there are times when using gradient descent is still preferable, just because it takes less time, and it also works really well. Okay, so are there any questions now about linear regression with multiple features, the closed form of linear regression? We're gonna, oh yes, go ahead.
So like, how are you gonna be using this stuff?
In like us?
Yeah.
So in the next lab, we're basically just gonna have you implement most of this stuff on a data set. We're gonna have you like just kind of write the code to do the gradient descent algorithm. We're gonna have like a collab. We're also gonna have you just code this equation up. Coding this is like really easy, right? You just take it and literally type that into Python. And then just see how that all happens just have you do that in a collab. Like for the actual pocket racer, we're going to be using like neural networks and stuff, so this isn't going to be as directly relevant, but you have to understand gradient descent in order to understand how neural networks work. Is there anything else? Okay, we're going to move on then from linear regression and talk about logistic regression.
Right. Hello, I'm back. So, part 4, logistic regression. So, we've been talking about linear regression this entire time because we've been under the impression that our input is going to be a number, our output will also be a number, and that range of numbers that we can produce an output in is continuous and basically spans the entire plane, the entire real number plane. It's a continuous variable, basically. There are no discontinuities anywhere from negative infinity to infinity. However, usually this is not the case. A lot of times we will have to do things that involve classifying discrete variables, such as in this picture, types of eggs. How would we go about doing that? Does anyone have any ideas? That's fine. So to put it more specifically, suppose we wanted to input the type of pan that we use and the time cooked, and get back the type of egg that we cook. The first step is figuring out how do we encode this information. So just for example, how do we encode the type of egg that we cooked if we have like 3 options? Any ideas?
0, 1, 2?
Alright, that's one idea.
Just like a vector with size, the number of like eggs, and then like a 1 for whichever class it is.
That's actually what people end up doing. It's called one-hot encoding. It's basically you make a Boolean category for every option, and you set it to 1 if that category is true and 0 otherwise. So there will only be one category that's enabled at a given time. And Jonathan, you bring up a good point. You asked why don't we just do it with like individual numbers? The reason is because if we do it like this, for example, 0 for hard-boiled, 1 for fried, 2 for scrambled, let's look at the implications of that. If we had 2 models, one of them guessed fried and the other one guessed scrambled, the correct answer is hard-boiled. The result is that the first model has a lower error value than the second, which doesn't really make sense in the context of classifying these, because ultimately both of the models are wrong. There's not really, one of them isn't less wrong than the other because it guessed a specific different category. So instead we do it the other way, where the error is going to be the same for anything that isn't the correct answer.
Okay, so now let's if we think about how we'd want to do this, right? We're gonna first look at a very simple situation where we're just doing a binary classifier where there's only 2 options. Say we want to decide is a is an egg yummy or is it not yummy? Right? It'll be 1 if it's yummy, 0 if it's not yummy. How would we solve this with linear regression, and what would be some problems that would come out of doing this? How do you think how would you go about trying to create a model, like a linear regression model for this?
Is that a trick question?
I mean, it's not going to work, but like think about how you do it, or it's not going to work well, but how would you do it, and what would be some problems with it, right? It's not a trick question. This is a.
You would have to pick like an arbitrary y value where it starts being yummy.
Yeah. So you'd have to do something like that, right? And what would be some error, like some problems with if you just said like, okay, if y is positive, it's yummy. If y is negative, it's yucky.
You can't do gradient descent?
Well, you could do gradient descent, but it would be kind of weird, like
meaningless.
yeah. So basically, there's a whole bunch of issues. So it would be hard to do gradient descent. If you had gradient descent, say 1 and -1, right? You'd get errors for overshooting. You could also take the output of your linear regression model and say put it through like a sine function. So like if anything were like positive, it would be set to 1. Anything that was negative would be set to -1. But then you can't differentiate the sine function to incorporate it into your gradient descent algorithm. So basically, this wouldn't work. We need something else. And so what we're going to use is actually the sigmoid function. So we're going to take the output of basically a linear regression model, and we're going to put it through this function, which is called the sigmoid function. And it gives us a value between 0 and 1. And since it's a value between 0 and 1, we can interpret this as a probability. So you could think about it as our model is giving us the probability that our egg is yummy. So then we also need, here's some examples of what this would look like. If you were to get a a large negative number, we'd be pretty confident that our egg is not yummy. And if it were a pretty large positive number, we'd be like, yes, this is yummy. And if we got 0, we're just totally not sure. It could be a good egg, it could be a bad egg. Now, also, we would need to update our, we're going to need to update our loss function. And so this is the new loss that we're going to use. Again, so y is the ground truth of what we're trying to predict, and y hat is what we've actually predicted. And if you look at this function, if y is 1, which means it is yummy, this value is going to be 0. So we're going to have 1, and then if y hat is close to 1, log of y hat is going to be very close to 0. But if it's but if y hat is smaller and closer to 0, then this is going to be a large negative number, which is going to make the loss really big. And then the same is true just in the inverse on this side, where if y is 0, then this value is going to be 0, etc., etc. And this is going to be the new loss function that we use. So now we're just going to add this all to gradient descent. We're still trying to find dl d theta, and we can use the chain rule to find this. So dl dy hat is going to be the gradient with respect. It's going to be the gradient of the sigmoid function. So that's going to be this right here. And then this dy hat of dx theta is going to be the gradient of, this is going to be the gradient of the loss function. So this is going to be this number. And then this dy hat with respect to dx theta is going to be the gradient of the sigmoid function. And then finally, this is just going to be the gradient we had from the linear regression part. So basically, we're just now multiplying all of these things together, and we're getting a new gradient for gradient descent, which we're going to so then we're going to update theta in the same way. Do you have any questions about how we're now modifying this for a binary classification model? Does everyone understand these equations? Yes.
So, but this is like still linear regression, or is it?
This is logistic regression.
Oh, okay.
Yeah. So when you're doing classification, you call it logistic regression.
Yeah.
Because we're no longer finding a linear model, right? The
Oh.
the sigmoid function isn't linear,
Oh,
right?
okay.
Okay. So this is how we do it in a binary case. If we're doing a non-binary case, say there's multiple classes we want. We're just gonna briefly touch on this. But if there's multiple classes, we're gonna first need to update our loss function, and we're gonna need to update. We're not gonna be able to use the sigmoid function anymore. Instead, we use something called the softmax function. So generally, if you're doing multi-class logistic regression, it's a lot easier to use like a neural network. It just feels it's just a lot more natural. And that's what we're going to be doing. We're not going to have you doing this. But when you use a network, you still use these equations. This to calculate the loss, and you use this on the outputs to find the probability of each class. So the softmax function and this loss function are very important. But yeah, they're just equations too, so we'll be able to reference this. Okay, now is there any questions on anything we've talked about so far? Okay. Solid. Yes.
Yeah, so after hearing about all that, you're probably a master at gradient descent now. You think, this stuff is really easy. Let's just apply gradient descent for all the training examples every single time. And if you do this, you probably use a gaming PC to write your code because those have graphics cards in them. Unfortunately, the majority of us do not, and so there are problems with applying gradient descent for all of the data points every single time. The main problem is that it's way too mathematically intensive to do that for every single data point. Like imagine a data set with 100,000 data points. You'd have to do all of those matrix multiplications and whatnot for every single point, and then average them all together, and it's not a great time. So what we typically do instead is something called mini-batch gradient descent. It's basically, we split up our data set into much smaller batches, and we perform the gradient descent on the samples in that batch, and we train based on that, and then we use a different batch the next time. So it's a little confusing because the gradient descent that uses all the data points at the same time, it's also known as batch gradient descent. That's not what we're talking about. We're talking about mini-batch gradient descent, which is smaller batches. I didn't name it. I don't know who did. There's also a more extreme example of this, known as stochastic gradient descent. The general idea here is that you're using a mini-batch, except your mini-batch contains only one sample. So what this means is that your gradient descent step might be more erratic. Like for example, if you randomly select one data point in your data set that has a really high error, then your gradient descent step is probably going to overcorrect, like correct more than it needs to. But in general, if you do this with all the data points and you do it a lot, eventually your gradient descent will still get to where it needs to be. This is of course the fastest to compute because you're only using one data point. This is also commonly used when data is arriving in real time in your training as you receive data. It's like, for example, a lot of like cloud applications will do this where people are working with the application, and while they're working with the application, the model trains itself with the data that it receives and updates the model accordingly. So it's pretty common. It's known as online learning when that's the case. So yeah. So of course, this is the impact of batch gradient descent. When your batches are really small, your updates are more like erratic. They change. They might overcorrect at times, undercorrect in other times. The general idea is the corrections will probably be more like uncertain, unpredictable. They'll eventually get to the same goal, usually pretty reliably, but larger batch sizes will eliminate that sort of random gradient descent, but it'll take longer to compute. So you have to pick a batch size that is effective at both actually like getting to the minimum quickly and doing so without all these crazy erratic steps, without requiring too much intensive computation. Oh, also to add, the batch size that you use when you're doing gradient descent is another example of a hyperparameter. It's something that you tune yourself while training your model.
Okay, so just to like take a step back really quick, and so when you're actually implementing these models, right, you're going to be taking your data. If you're doing just regular batch gradient descent, you're going to take all your data, you're going to use that to calculate loss. Remember, loss is going to sum over all your data. And then you're going to use the gradient descent to update all your weights. If you're using mini batch, you'll do this with smaller batches of data, right? And after each time, you're going to get an error, which you will use to update your weights, but you're also going to use it to figure out how well your model is doing. And so you'll use this. So this loss, which you can also call error, will be your training error that you're getting while you're training. And you might think it's really good to have a very small training error, like this person who spends way too much time training. However, that may not be the case. It could be the case that your model is overfitting. And this means that your model has become very good at making predictions about your training data, but it's not very good about making predictions about the overall population of data that your training data has come from. So this can be caused by a bunch of different things. If your data set's really small, it can be really easy for your model to just learn those 2 data points. Like you've got 2 data points, there's going to be a line between them for linear regression. It's going to be useless. If you train too much, this is especially true in neural networks, it can become over-tuned to your training data. If you have too many features, this could be a problem, and this kind of builds off of too many features. If your model is too complicated, it will be able to learn very fine details, and it will then tune itself to your training data way more than you'd like. So this is a little bit like someone who studies for a math test just by literally memorizing all the problems on a practice exam without actually understanding how to do the problems in the practice exam. And then getting to the exam and being like, oh shoot, this 4 is now 3, I don't know what to do. So how do we prevent this? Well, first of all, we measure it by using a test data set. So before we start training, we separate all of our data into a training data and testing data. And we train our data on the training data. And we do not use the test data ever for training. Because at the end, we will then use our test data to see if our model is actually good at predicting, if it will be good at predicting, other data from the population. So if our training error is really low, but our testing error is really high, we can assume that it's overfitting. And if they're both just really bad, then it is going to be underfitting, which basically just means the model is too simple and it's not really learning the patterns in the data. Overfitting would mean it's learning patterns that it shouldn't be. As I said, we can never use our test data when we're training our model. And so we have to do it at the very end. We shouldn't even use our testing data when we're tuning our model, because then we might tune hyperparameters to optimize for the test data, and we'll still have a slight form of overfitting. Instead, what we use is we use a validation data set, which we then separate further from the training data set. So we'll train our model on the training data, and then we will we'll test it on the validation data and see how good our model is. And if that looks good and we think our model is working well, we will then test it on the test data to make sure that it hasn't overfit to the training and validation data. Are there any questions on this? Sweet. So how are we actually going to implement this? So how are we actually going to implement this little training and validation loop? Is we're going to use something called k-fold cross-validation. And this basically means that we separate out some test data, then we're going to take our training data and separate that into k folds, or just chunks of data, and we're going to train our model from scratch several times. Each time we're going to withhold one fold as a validation data set. So say first time fold 1 is our validation data, folds 3 through 5 are our training data. So we'll train our model on those things, then we'll see what our error is on fold 1, and then we will retrain our model from scratch through folds 1 through 1, 3, 4, and 5, validate it with 2, find that error, and then we're going to take all that error, we're going to average it together, and then that's going to be how well our model performed. If we're happy with it, then we can try it. Then we can run it on the test data to make sure it hasn't to make sure it's doing well. Otherwise, we're going to go back and we're going to change some hyperparameters. We might change what kind of model we're using, et cetera, et cetera. Is there any questions on cross-validation? This is important. This is actually how you're going to be like training models, especially when we get to more complicated neural networks. Yeah. Okay. So if that makes sense, we're going to move on to a little bit on neural networks.
Hello again. So, it's big brain time, finally. We're talking about neurons. So first of all, we'll take a step back. What are neural networks? Basically, they are a learning algorithm, much like the regression stuff we've talked about, but they're a little bit fancier, and they're meant to model how the brain learns things. Of course, if you want to see how the brain works, you can just look up. It's right above your eyes. But anyway, neural networks are made of neurons. Each one acts like a modified logistic regression model. So each one does something that basically mimics what we talked about with respect to logistic regression. And the overall goal is to learn some data set in a manner that a simple regression, like a single regression line, cannot do. So neurons are made up of a lot of parts, and each of these parts has scary letters associated with it. We're gonna right now break down what these letters are. So this is the general diagram of everything. We start with the inputs and the weights. You guys have seen these before. Each neuron receives a certain number of inputs. We use n again. Each input, which is represented by x and then a subscript, you multiply that by a coefficient, w and a subscript. That's going to be the weight. Of course, as with anything, each weight and each input and weight are directly mapped. So there's only one. It's like a 1-to-1 ratio of inputs and weights. Next, you take the results of the previous step. Once you multiplied the inputs and weights, you add them all together. You also add a constant bias. So a lot of this stuff you've seen already. It's that you've seen the weights and the bias that we've added before for actual linear and logistic regression. So for example, if we took a 2-input neuron, we have 2 inputs, x1 and x2, 2 weights, w1 and w2. We have a bias, b, and to add them all together, it'll look like this. I'm not sure if you guys in the back can see, but it's x1 times w1 plus x2 times w2 plus b. If this looks familiar to you, you're probably thinking of the equation for a plane, which we showed earlier. It also has a bunch of coefficients. It has a bunch of input terms. Like earlier we had a, b, c, d. This is x1, x2, etc. And there's a bias without an input associated with it at the very end. For an n-input neuron, so if we have more than 2 inputs, those are the expressions. The first one, z up here, that's how you write it with a summation. It's basically just multiplying the inputs and weights together, adding them all up, and adding the bias. This is if you represent the inputs and weights as vectors, which is what we will do which is what actual neural networks do. So you take the input vector, it has a 1 in it because you have to multiply by the bias term. You have the weight vector, which has the bias in it, followed by the weights. And then you multiply them together using matrix multiplication. One of them needs to be transposed because in order to get the dimensions to match up, and your resulting value is the same as a dot product. Finally, once we have that sum, we have to pass that through the activation layer, and we pass it to the activation function, and then we get an output. This introduces nonlinearity into the system. We'll talk about what that means later, but for now we'll just cover some common activation functions. This is ReLU. It's basically 0 everywhere where x is less than 0, and when x is greater than 0, it's just x. This is sigmoid. We've already seen this. It ranges from 0 to 1 and kind of curves up so that it intersects the x-axis or the y-axis at y equals 0.5. So our output is going to look something like this. These two things are equivalent. This is our x vector, our weight vector. You multiply them together and you get this expression with the bias and all the terms. You pass that into an activation function, which is represented by sigma, and your output is y. That's it. So going back to activation functions, here are some more common ones along with the formulas. You don't really need to worry about like the exact specifics of one activation function versus the other. We'll talk about that probably later. But the main thing to understand is that none of these are lines, like they're all nonlinear. And the reason for that is that this is I think one of the fundamental like things you'll learn in linear algebra is that if you have an equation of a line and another equation of a line and you multiply them together, the result is still a line. And what this basically means is that if you have linear activations, no matter how many activations you pass your input through, it's always going to result in a linear result, which doesn't really make the model any more complex because all of those activations chained together are still just one line and can be represented as a single layer. This is why we use all these fancier functions that basically have more interesting things going on with them with respect to their distribution, how they pass through 0 and 1, if at all, basically how they map inputs to outputs.
All right, so now in the actual neural network we're going to actually put together a network, and we're going to create a network of several layers of neurons. Each layer is just going to be several neurons, and its output is going to be connected to the input of each neuron in the next layer. And likewise, all of its inputs is going to receive one input from each output in the previous layer. And in a fully connected layer, every neuron in one layer is connected to the one in the next. So that's why it's fully connected. Now, the first layer is just going to be the input layer. That's just going to be whatever your inputs are. They're usually represented as neurons, but we're not actually doing any operations here. You're just going to be passing them to the neurons in the first hidden layer, which is what the middle layers are called. And then you just say each of these neurons then pass their output to the next hidden layer, and then we pass it to the final output layer. The important, interesting thing about the output layer is while it is going to be, taking all of its inputs and applying a linear function to them, right, multiplying by the weights, adding the bias, it's not going to have an activation function at the end. The activation function is going to be something you're going to add to it. Because for example, you might want to take just a raw output if you want to do a linear regression type thing, like you might for this one. Or if this is a binary classifier, you might want to apply a sigmoid, in which case applying a ReLU would kind of shoot yourself in the foot, because you'd never be able to guess 0. All right, so forward propagation is the name of the algorithm. I guess before we start, is there any questions about neurons, how they're wired up? Okay, so forward propagation is the algorithm of when you have a fully trained or untrained. If you have a neural network and you want to pass data and get an output, the algorithm for getting the output is called forward propagation. So to start out with, you're going to apply your inputs. So we're going to follow this input in this top neuron. It's going to send its outputs to this first hidden layer. They're going to apply their operations, their activation functions, send it to the next layer. It's going to then each of these neurons is going to apply their operations, multiply the weights, add the bias, activation function, and then send that to the output layer. And then the output layer is going to take it, and you will take your output, do whatever you want with it, and there's your output. Are there any questions on this? Solid. We're going to make you do it now. Okay. The answers are here. That's fun. All right. Well, whatever. That's fine. So for this neuron, I guess the x will be the inputs to this neuron, and the inputs, as you can see, right, they're going to be just 5 and -4, and then I guess 1 won't really be an input, but this will be x will have 5 and -4, and then the 1 will be what you're using to apply the bias. These numbers are the weights, right? And then +4 is coming from the bias term. Does that make sense? Sweet. All right. hopefully we did not put answers. Okay.
Those are
Huh?
the weights for that.
Sure. Okay. Anyway, I guess if anyone that wasn't paying attention wants to say what the value is at that node. Like so what is this node going to be outputting? If using these two numbers, right, and assuming that we have a ReLU activation function, what is the output of this node going to be? It's like math, so I'll give you a second. Sure.
Yes, I can't add.
I think you're paying attention.
It's very possible I can't add.
Yeah? No? I mean, it's fine if you're wrong, because we're asking you to do like weird addition in your head. But I made the numbers, tried to make the numbers easy.
I think it's 1.
It is 1.
Yeah, and that is why I was hoping I was paying attention. Okay. Yes. All right. What are the outputs going to be of the entire thing? This one will like actually take a little while.
Yeah. Feel free to
so
get out paper, or just if you're sitting next to the whiteboard, use the whiteboard. But we're gonna make someone do it on here. We wrote it out on the whiteboard as well.
So
Someone will be our lucky guest or lucky winner for the day.
all right.
We should
People
randomly
doing
pick
that.
someone.
That sounds like fun. You like? What are you doing?
We're gonna get a spinner, like thinking online, and spin it in front of them.
Oh God. Okay.
Spinner.
Wait, what?
We're in the middle, we just
Go with that.
spinner.
Oh, it's
No,
Oh,
no.
they're physically
We're
spinning.
gonna add everyone's name.
Okay, wait.
It's like 1 out of 11 people. 1 out of 11
What's the?
This is so bad.
Input is 541.
Actually, yeah.
Weights is
What are
1.
so the weights are what's coming
So why can't I remove?
Oh God.
Here we go.
What do you mean weights
All
are?
right.
Which ones are the
So it's
weights?
-5 minus 4 plus 8.
Like what are the?
-1.
4 plus 8, so that's -1. Yeah.
I think it's the arrows pointing.
So 1 and 2. Oh
One.
yeah.
Dude.
For the other, so for the last
Speed.
like on top. 4 and 3.
Where?
Like the output, the top one.
Wait, you got what?
Oh, the top. 1.
Yes.
So it's just apply the same weights
weight to
again.
So it's 10 minus 4 minus 5.
What's your name?
Oh no, those are the inputs.
Right. Can you spell that?
They're already doing it, Prim.
What?
They're already doing it. We've been
Oh, on the
foiled.
board?
Yeah.
That's fun.
Well, it's because you took away the picture.
We'll put it back up in like a second.
This is where we got our weights from, so we're just
Sorry,
doing
yeah,
it.
yeah. Thank you. Alright. Evan?
Turn on extreme batteries.
Alright.
Is it out of battery?
Alright, it's coming.
You guys are almost out of battery.
Oh, okay. Well, that's okay. We're almost done.
How much out of that? How much almost?
It says turn on extreme battery saver.
Oh, 10%. That'll last like 5 minutes. Chilling.
Okay. All right. Well, I mean, they've already done it though. The wheel is done for Prim. We've been counting it.
And it's right there.
Oh, yeah. Nice job, Prim.
The math is wrong.
Yeah.
Well, no,
So
there's.
2 plus 2
Yeah.
minus 2 minus
Bro, what is with these?
I don't know.
Oh,
The animation got.
Because it's -1 times.
Why do you even have the animations? I don't understand.
What do you mean? What should I do?
Wait.
No, nothing. It's just
Why do you keep? Okay. So yeah.
minor skill issues.
All right. I don't know if we point our attention here. Remember, don't forget about the activation functions of the.
Oh, right. The inputs of the -1 is just 0. So it's the top one then becomes 1. So just add 3 to it.
Wait, you said what function?
The activation
Yeah,
functions.
the activation
Really?
function. So the negative number spits out 0 is there,
Yeah.
but
Yeah.
so no, not for the.
Oh,
So the -2 becomes 1. Just add 3 to it.
Oh wait, where?
The -2 at the top node becomes 1.
Okay,
Because
sure.
we
I don't know
don't
what that
subtract
is.
3.
Yeah.
And then the bottom one becomes -1, which we don't add 2.
Oh.
we forgot
Because yeah,
we forgot
because
the activation
yeah,
function.
because this would just become 0.
Yeah, it
Right.
spits out 0.
This would be 0, so then this thing would get, this would just be 2 minus 1 minus 2, 1, and then get negative 1.
We forgot that.
And then you have no rate. So yeah. Alright.
Yeah, you can put up the answer. Not that anyone hasn't seen it already.
Yes. So this is what the nodes look like. Is there any question or confusion or misunderstanding or like unclarity on like what this diagram means and how we got this? Yes.
So basically, the middle layer is like the hidden layer, right?
Yes. This is a hidden layer. It's the only one with any activation functions. Yeah.
In actual neural networks, you might have multiple hidden layers.
Yeah.
The negative becomes a 0 because the ray loop goes
Yeah.
into
Yeah. Exactly. Exactly. And there's no ReLU on the output. Okay.
Anyone else?
I'm a little confused on the last two values.
Okay, so like these two? So you understand how we got these, right?
Yeah.
So we pass one, so this value is getting 1, 0, and 1 as its inputs. It's multiplying 1 by 1, 0 by 3, and 1 by negative 1, right? So this is going to be 1, 1. These two are going to cancel out, and it's going to add a bias of 1. So it's going to be 0 plus or 1 minus 1 plus 1.
Okay.
That and then negative 1. Yeah, it's going to be 1 times 2 plus 0 minus 1 minus 2. It's going to be negative 1.
Anyone
Yeah.
else? Any questions on anything at all that we've covered in the last hour?
I think we're done. So thank you for coming to this lecture. Please fill out our fall quarter feedback form. Yeah, it's we'd love to hear your thoughts. If you want to include feedback for this lecture, you can do that too.
Yeah.
I think our last thing is just a 5. So
Yeah.
yeah, we'll leave the QR code. If you guys have any questions for us,
So we'll turn off
we
the
can hang
recording.
out for a little while. It's also